Good evening, students. Am I audible? Am I audible?
Yes,
Yes.
sir.
Okay. Okay. So let me start. So today our topic of discussion is group homomorphism and isomorphism. But I will not discuss this thing. Before discussing this thing, we need more knowledge on this function and everything. So let us complete our the function portion. So what we were discussing actually, so we are discussing this various type of functions. So I think I have already given you the definition of function, right? So I have given you the definition of function, that it is a relation with one restriction on it, correct? Do you remember what is the function, definition of function? You remember the definition of function? Do you remember? Anybody remember the definition of function? I have given the definition in the last class. Yes or no?
No, sir.
So you forget this thing. Okay, so let me remind you again that
Okay, sir.
the function or mapping is nothing but one special kind of relation. So what is it? So if A and B are two non-empty sets, so two sets are given to you, A and B. So then the relation F from set A to set B. So we are defining the relation. So we know what is relation. Relation is a subset of the cross product A and B. So it is a relation, that is this function is one kind of relation from set A to set B if every element of set A is associated with a unique element of set B. So that means it is a relation with the restriction that is every element of set A should be related with a unique element of B. So this is very important, that in this relation this element should be unique in the set B. So the function f from A to B is denoted by this symbol, that is we write, if we write down this symbol, that is we are defining the function f from the set A to set B. And the set A, so this set A is called the domain of the map or the function, and B is called the codomain of the map. So this set A is called the domain and this set B is called the codomain. And the set of all outputs. So when we are actually defining the function, then the set of all outputs. So if we have the function with us, so the collection of the elements in the set B, which are actually related to set A, is called the range of the function. So this was a picture, that is we have the domain here. So this is a set A and this is a codomain, and this is a range, that is only these elements are actually related to the all the elements of the set A. So that is in set in the codomain, sorry, in the domain. So there was one small example, that is set A and set B. So in the set A we can see that this A, B, C, D, all these four elements are actually related to these elements, that is P, Q, R only. But in the set B there are four elements, that is P, Q, R, S. So that means our domain is the set A and our codomain is the set B, but our range is the set containing the elements P, Q, and R. So range should be a subset of codomain. Here we have one more concept, which is if f is a function from A to B, and if x belongs to A, so that means if x is one element from the set A, and if we have the function f with us, then the element f of x, which belongs to the set B, is said to be the image of x, and the element x is called the preimage or argument of f of x under the map F. So these are the small concept we have with us. Now we have one example, that is multiplying let us multiply the natural numbers by 2. So if we multiply the natural numbers by 2, then what we get? So we get actually the set of even numbers. So that means our domain is set of natural number, and our codomain can be the set of natural number, can be the set of real number, can be the set of integers, but our range is the set is the even natural numbers. So our range is even natural numbers. So in this example, our domain is A is equal to set of natural number n, and the range B is 2x as x belongs to x. That means in the range what we have the set of even natural numbers only. So there is an example of image and pre-image. So hence for the image 100, so if we have the image 100, that means these hundreds can be written as 2 into 50, that means our pre-image is 50. Now we have some properties of a function. So what are the properties? The first property is every element of A must have image in B. So this is the first property, that every element of A must have image in B. So that means every element of A should be related to some element of B. So there is one picture we have, that is we have the set A. So this is a set A, and we have a set B. So you can see that A is related to D, B is related to E, C is related to F, but D is not related to anyone. But the definition says that every element of A must have image in B. So that means since every element, and here this D don't have any image in the set B, so that means this is not a function. So every element of A should have one image in B. So since this condition is not satisfied, so this figure does not represent any function. The second property is no element of A must have more than one image. So that means one element of the set A cannot related to more than one element in set B. So it should be related to one element of set B only. So we have one figure. So you can see in this figure A is related to D and B is related to E, F, N. So since this violates this property, that is no element of A must have more than one image. So that means it violates this property, that is this element has two image. So since this violates this property, so this is also not a function. So next property of the function is different element of A may have the same image in B. So this is another property, that is it may happen that more than two, that is two or more than two elements may have same image in the codomain. So in this example, you can see here we have B and C. Actually, they are related to an element E in the set B. So this may happen a function. So this is very important. That is, every mapping is a relation, but every relation may not be a mapping. So this is very important. That is, every mapping is a relation, but every relation may not be a mapping. So now, depending on different properties, we have different types of function. We are given these names depending on the nature of the function. So there are four types of function. So number one is one-to-one or injective. Number two is many-to-one. Number three, onto or surjective function. And number four is bijective function. So we have four types of function with us. Number one is one-to-one or injective function. Number two is many-to-one. Number three, onto or surjective function, and the last one is bijective function, which is the most important among these four. So now we have the definition with us. What are the definition of these functions? That is of these four types of functions. So the first it comes, that is one-to-one or injective function. So what is it? It says that if each element of the range of a mapping is paired with exactly one element of the domain of the mapping, then the mapping is known as one-to-one mapping. That means it says that in the range, what element you have, this element should be related to only one element. That is, each element of the range should be related to one element only in the domain. Then only we say that this is a one-to-one mapping. So here you can see there is a picture. So you can see that in the domain we have three elements, that is 1, 2, 3, that is in the set X. So this is our domain. And in the set Y, so this is our codomain, we have four elements, that is A, B, C, D. But in the range, that means what is the range? That is these elements in the domain, they are related to which elements? So these elements only is the range. So here 1, 2, 3, they are related to only three elements, that is A, B, and D. So that means these elements only makes your range. So this element A, B, and D, they are related only with exactly one element. Is A related to exactly one element, that is 3. B is related to exactly one element, that is 2, and D is related exactly with one element, that is 1. So it is a 1-1 mapping. Now we have the next function, which is known to us as many-to-one mapping. So as the name suggests, that means more than one element in the domain, they can be mapped to one element of the codomain. So what is the formal definition? If one element in the range is associated with more than one element in the domain, then this is called many-to-one mapping. That means it may happen that is more than one element, they can be related to one element of the codomain or the range. Then it is called many-to-one mapping. So there is a picture. So in this picture, you can check that we have two elements, that is A and C. They are actually related to one element, that is 2. So it may happen in the many-to-one mapping. So and this type of mapping is known to us as many-to-one mapping. So now we have the next definition, which is onto function or surjective function. So what is onto function or surjective function is? So the definition says a function f, which is defined from set A to B, is said to be onto function or surjective function if every element of set B there is a pre-image in set A. So look at the definition, that is every element in the set B, that is every element in the codomain must have one pre-image in the set A. So then it is called surjective function. So there is one picture we have. So we can see this is our set A, this is our set B. So set A, this is our domain and this is our codomain. So more than one element they can be related to one. So x and y. So this is a function. This may be a function. So this is a function obviously, and it is surjective if every element in V, that is 1, 2, 3, they have at least one pre-image in the set A. Obviously these elements 1, 2 and 3, they have pre-image, that is x, y, z, w in the set A, that is in the domain. So this is a surjection. But in the next picture you can see in the set B we have four elements, that is 1, 2, 3, 4. So since this element 4 in the codomain don't have any pre-image in the set A, so that's why this is not a surjective function or surjective mapping. Though if we consider this set A and the range 1, 2, 3, then it is a function. So we have one example with us. So what is the example? That is, we have two sets A and B, and we have the relation with us, that is F, that is written here as F, which is collection of the ordered pairs, that is 1, 2, 5, 4, 8, 2, 9, 4. So then you have to prove that F is a onto function. So to prove that this F is an onto function, we have to check that whether every element in the codomain set has one pre-image in the set A or in the domain. So you can check that in the codomain we have only two elements, that is 2 and 4. So we have to check that whether this 2 and 4 has one pre-image in the set A or not. So obviously 2 has a pre-image 1, 2 has also pre-image 8, 4 has a pre-image 5, and 4 has also a pre-image 9. So this is a onto function. So from the question itself, what we get? We get A is a collection of the, that is A is a set which contains 1, 5, 8, 9, and B is a set which contains elements 2 and 4, and F is a relation which contains the ordered pair 1, 2, 5, 4, 8, 2, and 9, 4. So all the elements on B has a pre-image on A, obviously, or we can say element 1 and 8 and 5 and 9 has the same image, that is 2 and 4 respectively. That means 1 and 4 they has the image 2, and 8 and 5 they has the image 4. So since this happens, so we say that this is a onto function. So therefore F, which is defined from A to B, is a surjective function. So now we have the most important type of function. So this is the most important, which is called the bijective function. So what is bijective function? So that means a function is said to be bijective when it is injective function as well as a surjective function. We can say when it is one-to-one mapping or onto map and onto mapping. When both of these are satisfied by the function, then it is called bijective function. So the definition is a function f which is defined from A to B is said to be one-on correspondence or bijective function. So this bijective function is also known as one-one correspondence if each element of A corresponds with a discrete element of B. So that means at first it should be a function. So if it is a function and if it happens that element of A correspond with a discrete element of B, so that means it should be injection first, the injective mapping, and every element of B has a pre-image in A. So that means it should be a surjective function. So that means if a function is injective as well as surjective, then it is called bijective mapping. Now we have one example with us. You can check the first condition, that is if every element of A corresponds with a discrete element of B. You can see obviously 1, 2, 3, and 4, they are the discrete elements in the set A, and they corresponds with the elements A, B, C, and D, which is discrete in the set B also. So this is first condition is satisfied, and the second condition is every element of B has a pre-image. So you can check that every element of B, they have pre-image in the set A. So this is a bijective function or mapping. So now how we can prove that a function, given a function, is a bijective or not. So we have to prove when a function is given to us, we have to check whether this is a bijective function or not. So how to check? So if we want to check a function is bijective or not, then we must compute the cardinality of the domain set, and we have to compute the cardinality of the codomain set. If this is equal, then we can go for the other check, that is we have to establish whether this function is injective or not, and then we have to establish whether the function is surjective or not. If this also happens, then we say that this function is bijective. So here let us discuss how to prove that a given function is bijective. If we want to find the bijections between two, first we have to define a map F such that A to B. So we have to define the map at first from the set A to set B, and then we have to show that F is a bijection. F is a bijection. By concluding that, what we should conclude? We should conclude at first that cardinality of the set A will be equal to cardinality of the set B. So cardinality also written as in this format, that is mod of A and mod of B. So these symbols are actually represent the cardinality of the set A, and that is cardinality of a set. So to prove F is a bijection, we should write down an inverse function for the F. So if it is possible that we can write down one inverse function of the function F, then it is very easy to show that it is a bijection. Or we can, what we can do, or we can show it in two steps. So what are the steps? Number one, we have to show that F is an injective function, and then we have to show that F is a surjective function. So that means if we can prove these two, then we can say that the function F is a bijective function. So now, if two sets A and B do not have the same size, there exists no bijection between them. Obviously, if they have different size, so there should not be one correspondence between them. So if the cardinality differ between the two sets, then we directly say that there should not any bijection. It is therefore often convenient to think of a bijection as a pairing up. So in bijection, what we actually consider, the pairing up. That is, each element of set A should pair with one element of codomain B. So in fact, if in A there are n number of elements and in set B there are n number of elements, then there exists n factorial bijection. So then there should be n factorial number of bijection between the set A and set B. So we have one example with us. So what example we have? We have a function fx equal to 3x minus 5, and we have to show that this function is bijective function from R to R.
Actually, I'm having some issues with my network. I will be joining from another device.
Okay, no problem.
Yeah.
So we have to show that the function fx, which is defined as 3x minus 5, it is a bijection. So how to show this? See, at first we have to check whether the domain of definition and the codomain has the same number of element. So from where to where actually we are defining? So can you please tell me what is the domain and what is the codomain here? Can anybody tell me what is the domain and what is the codomain in this function? Please tell me what is the domain and what is the codomain in the function fx equal to 3x minus 5. Yes. So R is the domain and R is the codomain here. So that means the cardinality of R is, we know that in R we have infinite number of elements. So the cardinality of domain and codomain, they are actually same. So then we can proceed further. So that means at first we have to show that this is an injective function. That means what we do when we show that it is an injective function. So actually we pick two different elements from the domain, and we assume that these two elements from the domain, they are actually mapped to the same element, and then we show that this only happen when these two elements are equal. So that means what we do, we pick two different elements from the domain and we assume that their image in the codomain are same. Then from this we show that this will only happen when the two elements, whatever we have assumed as to be different, we show that they are actually not different, they are same. That means we must prove that if fa is equal to c and ab equal to c, then a should be equal to b. So let us assume there exist two elements, two different elements, which actually maps to the element c. So that means we can write fa equal to c and ab equal to c. That means we can equate them. That means fa will be equal to fb. So that means fa equal to c will be equal to fb. So that means we have fa will be equal to fb. So if this happens, so that means what is our fa? Our fa is 3a minus 5, and what is our fb? Fb is 3b minus 5. So that means actually we are trying to say that this 3a minus 5 will be equal to 3b minus 5. So if we write these things, so what we have? We have 3a minus 5 will be equal to 3b minus 5. That means we have a will be equal to b. So any problem with this example? Till now, any problem?
No, sir.
So we have put that a will be equal to b. So if since a is equal to b, so that means this function is injective in nature. So now we have to show that this function is surjective also. So how to show this is a surjective function? So to prove the function is surjective, at first we should prove that for any point A in the range, so we should pick one element from the range. We should show that there exists a point B in the domain S such that f of B will be equal to A. So that means in the range, from the range, we pick one arbitrary element and we show that there exists at least one element in the domain such that it maps to that element. So let this A, so since B is mapped to A, so that means we can write that A will be equal to 3B minus 5. So if A is equal to 3B minus 5, so we can write this B will be equal to A plus 5 divided by 3. So what we have? We have the expression of B. So what is the expression of B? So our expression of B is A plus 5 divided by 3. So since we know that this A, this is a real number, this 5, this is a real number, and this 3, this is also real number. So that means whole operation, that is this, after adding to real number and then dividing by it another one real number, what we get? We get again one real number. So that means this is a real number and it should be unique if we consider this A is unique. So since this is a unique real number and it is in domain, so since this whole thing is again one real number, so this must be in the domain because our domain of definition of the function was the real number. So the function is surjective. So what we have proved? We have proved that the function is injective. We have proved that the function is surjective also. So then we can say that this function is bijective. So thus the given function satisfies the condition of one-to-one function and onto function, that is injective as well as surjective. So the function is bijective. So this is one practice problem. So any question in this of this function? Any question? Any doubt? Any question? Any doubt?
No, sir.
No, right? So now we are going to describe this thing. So what is it? It is group homomorphism and isomorphism. So at first we define the group homomorphism. So how, what is this group homomorphism is? So we know what is group. So what is group? How to write? What is a group? What is the group? What is group? I have given you the definition of group. What is group? Please tell me what is group.
So, group is a collection of individuals who interact with each other, like person to person, something like that.
Yes, that means group is nothing but it is one algebraic structure, that is you should have one set with you and one algebraic operation which satisfy four properties. So you know what are the properties is. So the properties are, it should be closure, it should be associative, it it should be, there should be one inverse, and one is associative, closure, inverse, and identity element. So if these four properties satisfy in the group with this operation with you, then we say that the set along with the operation is a group. So now what we have, what do we mean by homomorphism? So that means in homomorphism you should have two different groups, that is, let us write this as G, and this symbol is known to us composition. So G composition. So this is one symbol, you can symbolically it is written here, that is you have the set G with you and you have the operation that is composition, and you have another group that is H star, that is H is a set and star is the operation, so defined by you or by someone. So this is one operation you have, that is this operation actually satisfies these four properties of the group composition also here. So are two groups given to you, then suppose you have the map, you have one mapping, you know what is the mapping is right now. So if you have one map, actually one function we have with you, that is which is defined from the set G to set H, and this is called homomorphism, when it is called homomorphism from G composition to H star, if for all A comma B, so if you choose any element from the set G, that is A and B, and if you see that phi of A composition B will be is equal to phi A star phi B. So that means we have A from the set G, we have B from the set G. So this is a group with respect to the composition operation. So what will be A composition B, where this element should lie? This A composition B, where this element should lie? Where this A element should belong, that is A composition B. We have two elements A and B from the set G, and we have one operation, that is composition for the set G, and we say that this is a group. So where this element, that is A composition B, lies in G. So that means we have this element A composition B also in G. So now we are applying the function with what we have given. So this function is defined from G to H. So if we apply the function phi on the element, that is A composition, so where this element lies now, that is this phi A composition B. So where this element lies with this definition of, so this is our domain of definition and this is the codomain. So where this element lies, that is phi A composition B, where this element lie?
Sir, can you explain once more?
We have two elements A and B from the set G, and we know this G is a group with respect to the composition operation. So composition, that is, this is a notation. So we have this operation with us. So that means this A composition B, this also belongs to G. So now we have one function with us which is defined as from set G to set H. So now we have the element A composition B with us. Now if we apply the function phi, so then where this element belongs, that is phi A composition B, where this element belongs?
H.
H. So this is in H. Now we have A also with us from G. So where this element belongs? Phi A. Where this element belongs? Phi A. H. Where these elements belongs? This B belongs to G, and we are applying phi on this B, that is phi of B. So where this element belongs? Also from H. So this is an element in the set H. This is an element in the set H. So now we have the operation star in the group, that is H star. So where this element belongs, that is phi A star phi B. So where this element belongs? Yes, H. So this also belongs to H. So we can see that this element belongs to H, and this element that is in the right hand side also belongs to H. So we can equate them. So that means if it satisfies, that is phi of A composition B is equal to phi A star phi B, then we say that the function which is given to us, this is a homomorphism between these two groups. So let us take some example. So what we have with us, that is we have E dash is the identity element of H. That is we have this H is a group with some operation given to us, and this E dash is the identity element of H, and we have the map, which is map. So the map is given as phi G, phi such that G to H, that is this phi actually defines from set G to set H. How it defines? It defines that each element from the set G, it goes to the identity element. That is, if we apply the function to any element of the set G, then it actually goes to the identity element of the set H. So you have to prove that this is a homomorphism. So let us prove it. So what we have? Suppose we have uh, first element, first group is G composition, and another is H star. So we are defining that a function phi, which is defined from the set G to set H. How it is defined? That is, if we take any element from the set G, it actually belongs to E dash, where this E dash actually is the identity element of H. So you have to prove this is a homomorphism. So how to prove this is a homomorphism? That is, you have to show that phi of A composition B will be equal to phi of A star phi of B. So how to show? So since any element goes uh, to the identity element of H, so since A, B, this belongs to G, so this also implies that A composition B, this also belongs to the set G. So now, if we apply the function on this element, that is A composition B, so this should be belongs to H. So now what we have? We have this A composition B, this belongs to H, and A composition B, this belongs to G. So that means what we have? So since by definition any element from the set G, this actually goes to E dash if we apply the function on it. So actually this A phi of A composition B, this is actually E dash. So now what do we know again? We know phi of A. So since we are applying this function to any element, so A is arbitrary element from the set G, so this is equal to E dash, and this is also equal to phi of B, since B is any arbitrary element from set G. So now what we can write? We can write phi of A composition B, this is nothing but equal to E dash, that is identity element in the H. Now since this is identity element, so we can write this E dash nothing but is equal to E dash star E dash, because we know this is identity element, so we know the definition of identity element. So now what we have? We have phi of A equal to E dash, which is equal to phi B, so we can replace this thing, so it is phi of A star phi of B. So what it implies actually? It implies phi A composition B is equal to phi of A star phi of B. So we have proved this thing. So this was the proof of this, that is this called the trivial homomorphism. And we have one homomorphism again with us, that is the map. We have R and R star. What is R star? So R star is nothing but the positive real number. So how we are defining the homomorphism? We are defining X, that is we are choosing any element from the set R, that is set of real numbers, and we are applying the function. Then it maps this X to e to the power X, and we know that e to the power X cannot be negative. It should be some positive number. So that means it is actually the function from the set of real number to the set of positive real number. So this is also a homomorphism, that is you can check that e to the power. So since you know that e to the power X into e to the power X will be equal to e to the power X plus Y. Since this happens, so we know this is a homomorphism also. So I will come to this later. So this is actually congruence relation. So modulo function we have third example. So I will come to this later. So there are some example also with us. You can check, that is we have two function, different function phi1 and phi2, which is defined from the set R, that is real number, to T, so which is T is this kind of matrices. So now if phi 1 T gives, so if defined by this function, then you have to check whether this is a homomorphism or not. You can check this is also homomorphism. And phi 2 is defined something like that. Phi 2 T is e to the power T, so that is a matrix of order 2. That is e to the power T 0, 0 e to the power minus T. You can also check this is also from some homomorphism. And we have this homomorphism also, that is another map phi 3, which actually maps the real number to SO2. What is this SO2? So SO2 is matrix of order 2 which satisfy this relation. So phi 3T is given by this function. So if this is given by this function, then you have to check this is a homomorphism again. So this is it for today. So any question, any doubt?
Sir, can I repeat the proof?
Just a minute. Okay, so now your attendance link is open. So you can give your attendance through the link posted in your Google Classroom. Okay. So the proof again. So what we have? We have two groups, that is G composition and H star. So how it is given? The function is given to us, that is phi, which actually maps from set G to set H. How it maps? It maps any element from the set A, sorry, in the set G to the identity element of the group H. So since this is a group, we know that this is an identity element, and let us denote this identity element as E dash. So now we are choosing two arbitrary elements A and B. So since this is arbitrary element, and since this is a group, that is it is closed under composition operation, since it is given that G composition is group. So that means this A composition B, this also belongs to the set G. So now since this is one element again in G, so if we apply the function, so that means this phi of A composition B, this should be belongs to H. So since this is given by the definition of the function, so since this is belongs to H, and what is the definition of the function? That if any element from the set G, it goes to E dash. So we can write phi of A composition B, that should be E dash. And again, what we have? We have phi of A, so that is arbitrary element, any element we are choosing from the set G, so it also goes to E dash by definition of the function. And again, what we have? We had phi of B, this will be again equal to E dash. So now we can write phi of A composition B, this is equal to E dash. Since this is the identity element, so we can write this is nothing but, so this is the identity element of the set H. So what we can write? We can write that this is E dash star E dash. So now this E dash is nothing but, we can write this is phi of A, and this E dash can be replaced by phi of B. So that means ultimately what we have? We have phi of A composition B, which is equal to phi of A star phi of B. So this is the actually the definition of homomorphism. So if this satisfies, then we say that function is, that is these two group, that is G composition and H star is homomorphism. So this function defined there is a homomorphism. So since we saw that this satisfies this relation, so this is a homomorphism. Is it clear now?
Yes, sir.
Any other question?
No, sir.
So okay, so thank you. So we'll meet I think Tuesday.